Okay guys, the last video we reached to this point. We have the final expression for the magnetic moment, which is L E h bar over 2 mc. Now where L is values which are started from 0, 1, 2 up to n minus 1, where n is the principal quantum number and L is called the orbital angular momentum quantum number. Now from this equation 7 we see that this orbital angular momentum is an integral multiple of this quantity, and the quantity is E h bar over 2 mc, and this quantity is called Bohr magneton. So we express this quantity by mb, which is E h bar over 2 mc, and this is Bohr magneton. Now if we substitute the value of E h bar over mass times c, we get the value of Bohr magneton mb, which is 9.2741 into 10 raised to the power minus 21 arc Gauss inverse. It's the value of this Bohr magneton. Now since electron is a negative charge, has a negative charge, so the magnetic moment due to orbital motion of electron is now the magnetic moment due to orbital motion of electron is L times mb. But the charge on electron is negative, so we put a negative sign here, where L is the orbital angular momentum quantum number. Now Bohr magneton is the smallest constant in terms of which atomic and subatomic moments are measured. Now we have to calculate the ratio now. The ratio, which I represent by this G, the ratio of magnetic moment over orbital angular momentum, which is equal to, the magnetic moment is L E h bar over 2 mc over orbital angular momentum is L h bar. So we have this value G, which is equal to E over 2 mc, and its value is, if we put the numerical value, its value is 8.8 into 10 raised to the power 9 coulomb per kg, and this ratio is called gyrometric ratio. This ratio is called gyrometric ratio. Now I will explain a little bit more about this, what we call it, magnetic dipole moment, or magnetic moment. Suppose if we have a magnetic dipole moment, let's suppose we have an external magnetic field whose direction is shown here. This is the external magnetic moment, magnetic field, and I suppose it appears along y-axis. This is my z-axis and this is my x-axis. Now this is along y-axis. If we put a magnetic moment, a magnet inside the external magnetic field, which is making an angle theta with this magnetic field, here we have this magnetic moment mu. This is the z-axis and this is x-axis. Now y-axis, sorry. Now when a magnetic dipole moment mu is placed in an external magnetic field, this is the B external, it experiences a torque. This magnet experiences a torque which is given by tau, which is equal to magnetic moment times the cross product of magnetic moments and external field. Now this torque tends to ally this magnet in the direction of magnetic field. So the north pole goes towards the south pole and the south pole goes towards the north pole of this external magnetic field. Now maximum torque occur, like maximum torque occur when the theta between this external magnetic field and this magnetic moment is 90 degree. Now during this motion, like once this magnet is rotating around, ally itself in the direction of magnetic field, then there is a potential energy stored in this magnetic moment or this magnet, and that potential energy is given by delta E of this magnet, which is equal to minus times magnetic moment or the dot product of magnetic moments and external magnetic field. This will be equal to minus mu B external cosine of theta. So this is the potential energy stored in this magnet once it is inserting in an external magnetic field, such that during the time when it's ally itself in the direction of magnetic field, there is an energy stored in this magnet which is given by this relation. Now our next video is about magnetic moment due to spin. Magnetic moment due to